1935, Albert Einstein wrote a letter to a colleague that would haunt physics for the next 90 years. He was disturbed, deeply disturbed, not by the mathematics of quantum mechanics. He had helped create those mathematics, but by what those mathematics seemed to be telling him about the nature of reality itself. There was something in quantum theory that Einstein called spukhafte Fernwirkung, spooky action at a distance. He thought it was absurd. He thought it proved that quantum mechanics must be missing something, that the theory was incomplete, that there had to be some deeper explanation hiding beneath the surface of these strange equations. He was wrong, but not in the way you might think. The spooky action is real. We have now proven it beyond any reasonable doubt. Particles separated by vast distances truly do share an invisible connection that defies our everyday understanding of space and time. Yet Einstein was also right about something crucial. This connection, as bizarre as it is, cannot be used to send a message. It cannot be used to transmit information faster than light. It cannot violate the cosmic speed limit that his own theory of relativity established. This is the story of how physicists proved both of these seemingly contradictory things to be true. It is a story about gloves and coins and photons spinning in opposite directions. It is about experiments conducted in the basements of laboratories in Paris and across university campuses in the Netherlands. It is about a theorem written in 1964 that took decades to confirm, and about the three men who won the 2022 Nobel Prize for finally demonstrating what Einstein refused to believe. Most importantly, it is about why the universe lets us have the magic without the message. To understand what Einstein found so disturbing, you need to understand what quantum mechanics was telling physicists in the 1930s about the nature of particles. In our everyday world, objects have definite properties. A tennis ball sitting on a court has a specific location. It has a specific velocity, even if that velocity is zero. When you are not looking at the ball, you assume it continues to exist in a definite state. The ball does not become fuzzy or uncertain just because you turned your head. Reality, as we experience it, is solid and persistent. Quantum mechanics said no. At the scale of atoms and photons and electrons, particles do not have definite properties until you measure them. An electron does not have a specific position until you look for its position. A photon does not have a definite polarization until you pass it through a filter. The particle exists in what physicists call a superposition, a cloud of possibilities, a smeared out state that contains every potential outcome simultaneously. This alone was strange enough. But then came something even stranger. Sometimes, two particles can become entangled. They can enter a shared quantum state where their properties become correlated in a peculiar way. Take two electrons and prepare them so that their total spin must equal zero. Each electron can spin either up or down, but because the total must be zero, the spins must be opposite. One will be up, one will be down. But which one? Before you measure, neither electron has a definite spin direction. Both are in superposition. Both contain the possibility of being up and the possibility of being down. Yet they are linked, correlated, entangled. Now separate them. Send one electron to a laboratory in London and the other to a laboratory in Tokyo. Wait as long as you like, years if you prefer. Then measure the spin of the electron in London. Instantly, and this is the word that troubled Einstein, instantly the electron in Tokyo snaps into the opposite spin state, not in a microsecond, not at the speed of light, instantly. At the very moment you measure in London, something happens in Tokyo. Einstein presented this thought experiment in 1935 in a paper written with two colleagues, Boris Podolsky and Nathan Rosen. The paper's title was a question: can quantum mechanical description of physical reality be considered complete? Their answer was no. This instant correlation across arbitrary distances seemed to violate everything Einstein believed about causality and locality. No influence, he argued, should travel faster than light. Therefore, quantum mechanics must be missing something, some hidden variables that determine the outcomes in advance. The EPR paper, as it came to be known, was published in Physical Review on May 15, 1935. It caused an immediate sensation. The New York Times ran a story about it the day before it was published, after Podolsky leaked the contents to a reporter, much to Einstein's annoyance. Einstein had wanted the scientific community to engage with the physics, not with newspaper headlines. The paper was primarily written by Podolsky, based on discussions the three physicists had at the Institute for Advanced Study in Princeton. Einstein later expressed dissatisfaction with the final text, saying that the main point was, so to speak, buried by learnedness. He felt the argument could have been made more simply. The main point was this: if you accept that quantum mechanics is complete, that there are no hidden variables determining outcomes in advance, then you must accept instant action at a distance. When Alice measures her electron, Bob's electron instantaneously acquires a definite state, even if the electrons are on opposite sides of the galaxy. This violated what Einstein called local realism, the idea that objects have definite properties independent of measurement, and that influences propagate no faster than light. Niels Bohr, the father of quantum mechanics in many ways, responded to the EPR paper within months. His reply was dense and philosophical, and most physicists found it difficult to follow. The essential message was that Einstein was trying to apply classical concepts, like elements of physical reality existing independent of measurement, to quantum systems where such concepts do not apply. The debate between Einstein and Bohr continued for decades, mostly conducted through publications and occasional meetings at scientific conferences. They never reached agreement. Einstein went to his grave convinced that quantum mechanics was incomplete, that someday physicists would discover the hidden variables that explained everything. He was not alone. Many physicists of that era shared his discomfort with quantum mechanics. Erwin Schrödinger, who invented the wave equation that is the foundation of quantum mechanics, expressed similar concerns. In a letter to Einstein shortly after the EPR paper appeared, Schrödinger introduced the term entanglement, in German Verschränkung, to describe the phenomenon. He called it not one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Schrödinger was as disturbed by entanglement as Einstein was. He invented his famous thought experiment about the cat in a box precisely to illustrate how absurd quantum superposition seemed when applied to everyday objects. But unlike Einstein, Schrödinger accepted that quantum mechanics worked even if he could not make philosophical peace with it. Think of it this way. Imagine you have a pair of gloves, one left-handed, one right-handed, and you put them in separate boxes. You send one box to London and one to Tokyo. When someone opens the box in London and finds a left-handed glove, they instantly know the box in Tokyo contains a right-handed glove. But there is nothing spooky about this. The gloves had their handedness all along. The correlation was built in when they were put in the boxes. Einstein believed quantum mechanics must work the same way. The electrons, he argued, must carry hidden information that determines their spin direction before any measurement is made. The measurement merely reveals what was already there. Quantum mechanics describes our ignorance, not reality itself. For nearly 30 years, this remained a philosophical debate. Einstein died in 1955, still convinced that quantum mechanics was incomplete. Most physicists shrugged and continued using the equations, which worked extraordinarily well, without worrying too much about what they meant. The founders' debate was treated as philosophy, not physics. Then, in 1964, a physicist working at CERN changed everything. John Stuart Bell was born in Belfast in 1928. He worked primarily on particle physics, but he had a side interest that would prove to be his greatest contribution to science. He wanted to understand what quantum mechanics was really telling us about nature. Bell asked a question that seems obvious in retrospect, but that no one had properly formulated before. Is there any way to experimentally distinguish between Einstein's hidden variable theory and standard quantum mechanics? Is there any measurement we could make that would give different results depending on which theory is correct? He found that there was. Bell's insight was subtle, but profound. Consider again our two entangled electrons, one in London and one in Tokyo. Each laboratory can measure the spin of its electron along any axis it chooses, up-down, left-right, or any angle in between. Bell showed that if Einstein was right, if the electrons carry hidden information that predetermines their spin in all possible directions, then the statistical correlations between measurements in London and Tokyo must obey certain mathematical limits. These limits are now called Bell inequalities. Here is the key insight, explained simply. Imagine Alice is in London and Bob is in Tokyo. They each independently choose an axis along which to measure their electron spin. They do this over and over again with many entangled pairs, choosing their measurement directions randomly each time. Afterward, they compare their results. If hidden variables determine the outcomes, there is a limit to how correlated their measurements can be. Think of it like a game. If Alice and Bob are each secretly consulting a pre-arranged instruction book to decide their answers, there is a maximum score they can achieve through that strategy alone. Bell calculated this limit. If you measure along 3 carefully chosen axes, hidden variable theories predict you will get matching results at most 67% of the time. But quantum mechanics predicts something different. It predicts you can get matching results 75% of the time. The quantum correlations are stronger than any hidden variable theory can explain. This was no longer philosophy. This was a testable prediction. If experiments showed correlations above 67%, Einstein was wrong. If they stayed below, quantum mechanics was wrong. Bell published his theorem in a short-lived journal called Physics Physique Physica on November 4, 1964. Almost nobody noticed. He accumulated fewer than a dozen citations in 6 years. Many physicists who did notice dismissed the work as irrelevant. Quantum mechanics was already well tested. Why bother with this foundational navel-gazing? The paper itself was elegant and compact, only 6 pages long. Bell began by summarizing the EPR argument, then proceeded to derive his inequality with mathematical precision. The key equation was deceptively simple. If hidden variables determine the outcomes of measurements, then the correlation function between distant measurements must satisfy certain bounds. Quantum mechanics predicted correlations that exceeded these bounds. The most important sentence in the paper was this: in a theory in which parameters are added to quantum mechanics to determine the results of individual measurements, without changing the statistical predictions, there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument, however remote. In other words, Bell had identified a sharp either-or. Either quantum mechanics was wrong about the correlations it predicted, or the universe was genuinely non-local. Distant events could be correlated in ways that no local mechanism could explain. But Bell had given experimentalists a target. All someone had to do was build the apparatus and make the measurements. The first serious attempt came in 1972. John Clauser, a young physicist who had become obsessed with Bell's theorem as a graduate student, built an experiment at the University of California, Berkeley, with Stuart Friedman. They used pairs of photons rather than electrons. Photons were easier to work with and measured their polarizations at different angles. Clauser's path to this experiment was not easy. As a graduate student at Columbia, he had tried to interest faculty members in testing Bell's inequality. The response was largely indifference or hostility. Quantum mechanics worked. Why question it? He found a more welcoming environment at Berkeley, where physicists Charles Townes and Howard Shugart supported his unconventional research. Clauser later recalled that Townes told him, "Well, it's sort of crazy, but why not?" That was enough encouragement. The experiment used calcium atoms that were excited by ultraviolet light from a mercury arc lamp. When the atoms de-excited, they emitted pairs of photons in what is called a cascade transition. These photon pairs were entangled. Their polarizations were correlated. Clauser and Friedman placed polarizers on each side of the apparatus, set at various angles. They counted coincidences, instances when both detectors registered a photon at nearly the same time, indicating that both photons from an entangled pair had been detected. The results violated Bell's inequality. The correlations were too strong to be explained by hidden variables. Quantum mechanics was right, but there was a catch. Actually, there were several catches. These are what physicists call loopholes. The first loophole concerned the detectors. Clauser and Friedman could not detect every photon pair. Many photons were lost or missed. This opened the possibility that the detected photons were somehow special, a biased sample that happened to show stronger correlations than the true population. Maybe hidden variable advocates argued the lost photons would have shown weaker correlations that brought the total below Bell's limit. This is called the detection loophole. The second loophole was more subtle and more troubling. In Clauser's experiment, the measurement settings, the angles at which the polarizers were oriented, were fixed before the photons left the source. This meant that, in principle, the photons could have known what measurements awaited them. The hidden variables could have been influenced by the experimental setup in a way that mimicked quantum correlations without violating locality. This is called the locality loophole. To close the locality loophole, you would need to change the measurement settings after the photons were already in flight, so fast that no information could travel between the two detectors to coordinate the results. The choice of measurement at one detector would need to be made so late that even a signal traveling at the speed of light could not reach the other detector in time to affect its outcome. This was what Alain Aspect set out to do. Aspect was a French physicist working at the Institut d'Optique in Orsay, on the outskirts of Paris. In the late 1970s, he began designing a series of increasingly sophisticated experiments to test Bell's inequality while closing the loopholes that plagued earlier work. Before he began, Aspect made a pilgrimage to Geneva to meet John Bell at CERN. He wanted Bell's blessing for his experimental program. Bell listened as Aspect explained his plans, then asked that famous question, "Do you have a permanent position?" When Aspect confirmed that he did, Bell encouraged him to proceed. Bell's concern was not idle. Testing the foundations of quantum mechanics was considered a backwater of physics, if not outright crankery. Serious physicists worked on particle physics, condensed matter, or other respectable fields. Questioning whether quantum mechanics was correct, when it had been confirmed by countless experiments, seemed pointless at best and career suicide at worst. Aspect's first experiments, conducted in 1981 and 1982 with collaborators Philippe Grangier and Gérard Roget, improved upon Clause's design with better photon sources and more efficient detectors. They used calcium atoms excited by a 2-photon laser process, which produced entangled photons at much higher rates than the arc lamp method. This allowed them to collect more data and achieve higher statistical significance. The first 2 experiments were impressive. They violated Bell's inequality by many standard deviations, far more decisively than Clause's original work. But they still suffered from the locality loophole. The measurement settings were fixed before the photons left the source. But his third experiment, published in Physical Review Letters in December 1982, was the breakthrough. Aspect's innovation was an acoustic optical switch, essentially a device that could flip a photon's path between 2 different polarizers extremely rapidly. The switches operated at frequencies near 50 MHz, changing the measurement setting about every 10 nanoseconds. This was faster than light could travel between the 2 detectors. The switches worked using ultrasonic waves in water. When a high-frequency sound wave passed through the water, it changed the refractive index in a periodic pattern, creating a kind of diffraction grating for light. By turning the sound wave on and off, Aspect could redirect photons between 2 different paths, each leading to a polarizer set at a different angle. Here is what made this so important. In Aspect's experiment, the 2 detectors were separated by about 12 meters. Light travels 12 meters in about 40 nanoseconds. But the switches were changing the measurement settings every 10 nanoseconds, and these changes were random, or at least pseudo-random, driven by independent oscillators on each side that ran at slightly different frequencies. This meant that the setting at one detector could not possibly have influenced the outcome at the other detector. There was not enough time for any signal, even one traveling at light speed, to carry the information. The experiment was technically demanding. Everything had to be synchronized with nanosecond precision. The photon counters had to register individual photons reliably. The switches had to operate fast enough to change during the photon's flight time, which was only about 40 nanoseconds. The results were clear. The correlations violated Bell's inequality by 5 standard deviations. The measurements at the 2 detectors were correlated more strongly than any local hidden variable theory could allow. Einstein's dream of a local, realistic universe, one where objects have definite properties independent of measurement and where influences propagate no faster than light, was dealt a severe blow. The world, at its most fundamental level, was stranger than he had wanted to believe. What did Aspect's experiment prove exactly? It proved that any theory explaining the correlations between entangled particles must violate at least one of 2 assumptions that seem almost self-evidently true. The first assumption is realism. Physical systems have definite properties, whether or not anyone measures them. A tennis ball has a position even when no one is looking at it. An electron has a spin direction even before it enters a detector. The second assumption is locality. An event in one location cannot instantly affect events at a distant location. Information, influences, and causes must propagate through space at finite speed, never faster than light. Einstein believed both assumptions. They matched his intuition about how the universe should work. They matched the framework of his theory of relativity, which was built on the impossibility of faster-than-light signaling. Bell's theorem showed that quantum mechanics violates at least one of these assumptions. Aspect's experiment showed that the real world agrees with quantum mechanics. Therefore, the real world violates at least one of these assumptions. Which one? This is a matter of ongoing debate among physicists and philosophers. Most working physicists accept that realism must be abandoned. Particles do not have definite properties until measured. Some argue that locality must be abandoned instead. There really is some kind of faster-than-light connection between entangled particles, even though it cannot be used to send signals. A few maintain that both assumptions are wrong. What is not debated is the experimental result. The correlations are too strong. Hidden variables do not work. Einstein was wrong about the nature of quantum reality. Aspect later described meeting John Bell before beginning his experiments. He was a doctoral student, nervous about pursuing such an unfashionable topic. Bell's first question was practical. Do you have a permanent position? When Aspect said yes, Bell encouraged him to proceed. The question reflected the reality that questioning the foundations of quantum mechanics was not considered respectable physics. Aspect risked his career to conduct these experiments. The risk paid off. Aspect's work is now recognized as one of the most important experiments in the history of physics. In 2022, he shared the Nobel Prize in Physics with John Clauser and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. But the story was not over. Aspect's experiment closed the locality loophole, but it did not close the detection loophole. Other experiments closed the detection loophole, but left the locality loophole open. For decades, no single experiment managed to close both simultaneously. This mattered because the loopholes, however implausible they seemed, represented logical escape routes for those who wanted to preserve Einstein's vision. Perhaps the lost photons really were conspiring to hide the true correlations. Perhaps there was some subtle connection between the photon source and the measurement devices that created the illusion of quantum non-locality. In 2015, a team led by Ronald Hansen at Delft University of Technology in the Netherlands finally performed what is called a loophole-free Bell test. The Delft experiment was a marvel of engineering. 2 electrons were trapped in diamond crystals containing what are called nitrogen vacancy centers, tiny defects in the crystal structure that hold an electron in place. A nitrogen vacancy center is created when a nitrogen atom replaces a carbon atom in the diamond lattice next to an empty space where another carbon atom should be. This configuration can trap a single electron whose spin can be manipulated and measured with high precision. These 2 diamonds were located in separate laboratories 1.3 kilometers apart on the Delft campus, one in a building called the Applied Sciences Building, the other in a building known as the Reactor Institute. A third laboratory, housing the critical beam splitter, was located between them. The separation was crucial. 1.3 kilometers is far enough that a light signal traveling from one lab to the other would take more than 4 microseconds. The measurement on each electron took only about 4 microseconds as well. The researchers had to be extraordinarily careful about timing. They had to ensure that the random choice of measurement setting at one lab was made after any possible light speed signal from the other lab could have arrived, yet before the measurement was complete. To achieve this, they used random number generators based on a process called spontaneous emission, photons randomly emitted by atoms. These random numbers determined which measurement each lab would perform on its electron. The timing was controlled to nanosecond precision by atomic clocks. But how do you entangle 2 electrons that are more than a kilometer apart? This was the ingenious part. Each electron was first entangled with a photon at its local lab. When an electron in a nitrogen vacancy center is excited with a laser pulse, it can emit a photon whose polarization is entangled with the electron's spin state. This is a well-understood process that happens reliably. Then the 2 photons were sent through optical fibers to the third lab located midway between them. At this central lab, the photons were measured together in a way that transferred the entanglement to the distant electrons, a technique called entanglement swapping. When the central lab detected both photons in a particular joint quantum state, the 2 electrons became entangled, even though they had never interacted directly. This entanglement swapping succeeded only about once every 156 million attempts. Most of the time, one or both photons were lost in the optical fibers, or arrived at slightly the wrong time, or the joint measurement at the central lab did not yield the right result. The experiment ran for 220 hours over 18 days and produced just 245 successful trials where entanglement was confirmed and both electrons were measured. But those 245 trials were enough. The correlations violated Bell's inequality. Both loopholes were closed simultaneously. The results rejected local hidden variable theories with a p-value of 0.039, meaning there was only a 3.9% chance that the observed correlations could have arisen by chance in a local realistic universe. 2 months later, 2 other groups, one led by Anton Zeilinger at the University of Vienna and one at the National Institute of Standards and Technology in the United States, published their own loophole-free Bell tests using different experimental approaches. All 3 experiments agreed quantum mechanics was correct and local hidden variables were ruled out. It is one of the few experiments in physics that can directly test and even reject fundamental principles of nature, Hansen said after the experiment was published. The 80-year-old debate that Einstein had sparked was finally settled experimentally. The spooky action was real. Now comes the paradox that this entire documentary has been building toward. If entangled particles really do share an instantaneous connection, if measuring one particle truly does affect its distant partner faster than light could travel between them, then why can we not use this to communicate faster than light? This is not an academic question. If we could send information instantaneously across any distance, the implications would be staggering. Interstellar communication would become trivial. The fundamental structure of space and time would need to be reconsidered. The basic framework of physics, where causes precede effects and information propagates at finite speed, would collapse. But we cannot. And the reason is built into the very fabric of quantum mechanics. Let us return to our entangled electrons, one in London with Alice and one in Tokyo with Bob. They have agreed that the electron spin will encode a message. Spin up means 1, spin down means 0. Alice wants to send Bob a binary message. Alice decides to send a 1. She measures her electron along the up-down axis. Half the time, she gets spin up. Half the time, she gets spin down. The outcome is completely random. She has no control over what result she gets. This is a fundamental feature of quantum mechanics. Measurement outcomes are probabilistic, not deterministic. Imagine Alice desperately wants her electron to come up, spin up so she can send a 1 to Bob. She prepares her measurement apparatus, aligns it carefully along the vertical axis, and measures. Nature gives her whatever nature feels like giving her. Spin up or spin down with equal probability. She cannot influence this. She is not choosing the measurement outcome. She is only choosing to make a measurement. But wait, you might think. When Alice measures and gets spin up, Bob's electron instantly becomes spin down. He can measure it and know that Alice got spin up. Is that not communication? No. Here is why. Before Alice measures, Bob's electron is in superposition, a quantum state that contains both spin up and spin down as possibilities. After Alice measures, Bob's electron has a definite spin, the opposite of whatever Alice got. But from Bob's perspective, nothing has changed that he can detect. If he measures his electron without knowing what Alice did, he still gets spin up 50% of the time and spin down 50% of the time. The statistics he sees are identical whether or not Alice has measured her electron. Think about this carefully. Bob measures his electron and gets spin down. What does this tell him? He does not know if Alice has measured yet. If she has, then her electron is definitely spin up. The measurement collapsed the entangled state. If she has not, then her electron is still in superposition. The entangled state is still intact, and Bob's measurement just collapsed it. But Bob has no way to distinguish these two cases by looking at his measurement result alone. He got spin down. This could mean Alice measured first and got spin up, or it could mean he measured first and his measurement collapsed the entangled state, leaving Alice's electron to be spin up when she eventually measures. From Bob's perspective, the result looks exactly the same either way. He just got a random outcome with 50-50 odds, exactly as quantum mechanics predicts, regardless of what Alice does or when she does it. Alice cannot encode a message because she cannot control her measurement outcomes. She cannot force her electron to be spin up when she wants to send a 1 and spin down when she wants to send a 0. The outcomes are random. All she can do is observe what nature gives her. Bob cannot decode a message because the statistics he sees do not change based on Alice's actions. His measurement outcomes are distributed exactly the same way whether Alice has measured or not, and whether Alice chose to measure along the up-down axis or some other axis entirely. This is the content of the no communication theorem, proven rigorously by physicists in the late 1970s and 1980s. It states that quantum entanglement cannot be used to transmit classical information. No matter how clever your scheme, no matter how you manipulate your entangled particles, you cannot use them to send a message faster than light. Perhaps you are thinking of a workaround. What if Alice and Bob do not just make single measurements, but coordinate their activities in some clever way? This is exactly what physicists have tried again and again for decades. Every scheme fails, and they all fail for the same fundamental reason. Consider one clever-sounding scheme. What if Alice chooses whether or not to measure her electron, and Bob tries to determine from his measurements whether Alice measured or not? If Alice measures, Bob's electron has a definite spin. If Alice does not measure, Bob's electron is in superposition. Surely Bob can tell the difference? He cannot. When Bob measures his electron, he gets a definite result either way, spin up or spin down. He cannot tell whether his electron was already in that state because Alice measured first, or whether his measurement collapsed a superposition. The mathematical structure of quantum mechanics guarantees that these two scenarios are indistinguishable from Bob's perspective. Here is another scheme. What if Alice measures along different axes depending on the message she wants to send? Measure along the vertical axis to send 0, along the horizontal axis to send 1. Bob can then measure along some clever combination of axes to figure out which choice Alice made. This also fails. When Alice measures along the vertical axis, Bob's electron is left in one of two vertical spin states, up or down, each with 50% probability. When Alice measures along the horizontal axis, Bob's electron is left in one of two horizontal spin states, left or right, each with 50% probability. But these probability distributions look the same to Bob when he measures. No matter what axis Bob chooses for his measurement, his outcomes are 50-50, regardless of which axis Alice chose. In 1982, a physicist named Nick Herbert published a paper proposing a superluminal communication device using quantum entanglement. The scheme was clever. It relied on being able to make copies of quantum states. If Alice could clone her half of the entangled pair many times, she could make enough measurements to determine whether her particle was in one state or another, and somehow encode this information for Bob. The paper was wrong, but refuting it led to an important discovery. 3 different physicists, William Wouters and Wojciech Zurek working together, and Dennis Deeks independently, proved that quantum states cannot be cloned. You cannot take an arbitrary quantum state and make an exact copy of it. The act of trying to copy it necessarily disturbs it. This is called the no-cloning theorem, and it has profound implications. The title of Wouters and Zurek's 1982 paper in Nature said it all. A single quantum cannot be cloned. John Wheeler, the legendary physicist, suggested that memorable title. The story behind the no-cloning theorem is worth telling. Herbert's paper was submitted to a journal and sent out for peer review. One of the referees, Giancarlo Girardi, recognized that the scheme could not work and essentially proved the no-cloning theorem in his referee report, but he did not publish this proof separately, perhaps thinking it was too obvious to warrant a paper. When Wouters and Zurich, and independently Dieks, published their proofs a few months later, it became a landmark result. The physicist Asher Perez later reflected on this episode. With some hindsight, it is now clear that Herbert was using an argument which was clearly wrong, but by pointing it out, an important new result was discovered. This is often the way physics progresses. Someone makes an error, others correct it, and new knowledge emerges. The no-cloning theorem blocks Herbert's scheme and every scheme like it. If you could clone quantum states, you could use entanglement to communicate faster than light. But you cannot clone quantum states. Therefore, you cannot use entanglement to communicate faster than light. Notice the structure of this argument. The inability to copy quantum information and the inability to communicate faster than light are not separate facts. They are connected. The no-communication theorem implies the no-cloning theorem, and vice versa. They are two faces of the same deep truth about the quantum world. But perhaps there is another way. What about quantum teleportation? You have heard of this. The ability to transfer a quantum state from one location to another, seemingly instantaneously, using entanglement. Scientists have demonstrated quantum teleportation over hundreds and even thousands of kilometers. Surely this must involve faster than light information transfer. It does not, and understanding why reveals something beautiful about the structure of quantum mechanics. The idea of quantum teleportation was first proposed in 1993 by a team of 6 physicists: Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Jozsa, Asher Perez, and William Wouters. Their paper, published in Physical Review Letters, showed that entanglement could be used to transfer the complete quantum state of a particle from one location to another, without physically moving the particle itself. Here is how quantum teleportation works. Alice has a particle in some quantum state that she wants to send to Bob. This state might be a superposition of spin up and spin down, with specific amplitudes that encode information. Alice does not know what these amplitudes are. She cannot determine them by measurement without destroying the state, but she wants to transfer the state to Bob intact. Alice and Bob also share a pair of entangled particles that were prepared earlier. They each hold one particle from this entangled pair. Now Alice has 2 particles: her original particle, whose state she wants to teleport, and her half of the entangled pair. Bob has just 1 particle, his half of the entangled pair. Alice performs a joint measurement on her 2 particles, the original and her half of the entangled pair. This is a special kind of measurement called a Bell state measurement, which determines how the 2 particles are correlated with each other. There are 4 possible outcomes of this measurement, and which outcome Alice gets is completely random. Here is the crucial step. Alice must tell Bob which outcome she got. She must send him 2 classical bits of information, a message that travels at the speed of light or slower through ordinary communication channels like radio waves or optical fibers or telephone calls. When Bob receives this classical message, he uses the information to perform an operation on his half of the entangled pair. If Alice got outcome 1, Bob does nothing. If she got outcome 2, Bob flips his particle's spin. If she got outcome 3, Bob performs a different rotation. If she got outcome 4, yet another rotation. The specific operation depends on which of the 4 outcomes Alice reported. And miraculously, after Bob performs the correct operation, his particle is now in the exact state that Alice's original particle was in. The quantum state has been teleported. Alice's original particle no longer has that state. The measurement destroyed it. But Bob's particle now carries the complete quantum information. But notice, the teleportation is not complete until Bob receives Alice's classical message. Without that message, Bob's particle is in a random state that tells him nothing about Alice's original particle. The quantum information travels only as fast as the classical message that accompanies it, which is to say, no faster than light. This is a subtle point that science fiction often gets wrong. In popular depictions, quantum teleportation is instantaneous. The particle disappears here and appears there in the blink of an eye. In reality, quantum teleportation is limited by the speed of light, just like everything else. The name teleportation is itself a bit misleading, chosen for dramatic effect rather than accuracy. Nothing is physically transported. Instead, the quantum state is reconstructed at a distant location using the resources of entanglement and classical communication. The particle does not travel, only its state is transferred. The 1993 paper that introduced quantum teleportation made this explicit in its title: Teleporting an Unknown Quantum State via Dual Classical and Einstein-Podolsky-Rosen channels. The dual channels are essential. The quantum channel, the entanglement, and the classical channel, the ordinary message, must both be used. Neither alone suffices. One of the authors of that paper, Asher Perez, was once asked by a journalist whether quantum teleportation meant we could teleport people, like in Star Trek. Perez replied that quantum teleportation can transfer the complete state of a quantum system, but that the transfer requires a classical message, which is limited to light speed. No instantaneous human teleportation. No faster than light communication. There is another important point. Quantum teleportation destroys the original state. When Alice makes her Bell state measurement, her original particle is no longer in the state she wanted to teleport. The information is not copied. That would violate the no-cloning theorem, but transferred. This is sometimes called the no-deleting theorem in reverse. If you could teleport without destroying the original, you would have cloned a quantum state, which is impossible. The no-communication theorem has been tested and confirmed. The loophole-free Bell experiments that proved entanglement is real also confirmed that the correlations cannot be used to signal. This is because the theorem is not a separate add-on to quantum mechanics. It is a direct consequence of the theory's mathematical structure. The mathematics works like this. When Alice makes a measurement on her entangled particle, she changes the joint quantum state of the two-particle system. But the reduced state that describes Bob's particle alone, the state that determines what outcomes he will see when he measures, does not change. This is a mathematical fact that follows from the linearity of quantum mechanics. In physicists' jargon, Alice's local operations cannot change Bob's local density matrix. She can do anything she wants to her particle, measure it, rotate it, feed it through any quantum gate, and Bob's measurement statistics remain unchanged. He cannot tell by any local measurement what Alice has done. This result does not depend on any particular interpretation of quantum mechanics. Whether you believe the wave function is real or that measurements create reality, or that all possible outcomes happen in parallel universes, the no communication theorem holds. It is built into the mathematics at such a fundamental level that no interpretation can escape it. The theorem was first proven in various forms in the late 1970s and 1980s. Philippe Eberhard at Lawrence Berkeley National Laboratory provided one of the earliest rigorous proofs in 1978, showing that faster-than-light communication was impossible using any phenomena describable by quantum field theory. Later proofs by Girardi and others extended the result to cover all possible measurement schemes. This is sometimes called signal locality or no signaling. It is a weaker condition than Einstein's original locality. The correlations between Alice and Bob do violate Einstein locality, but it preserves causality. Causes still precede effects. Information still propagates at or below the speed of light. The universe maintains its logical coherence. There is something almost uncanny about this situation. Quantum mechanics gives us correlations that are stronger than any classical theory can explain, strong enough to prove that hidden variables do not exist, strong enough to win Nobel Prizes. Yet it withholds from us the ability to use those correlations to send messages. The correlations are real. The connection between entangled particles is real. When you measure one particle, something happens to the other particle that cannot be explained by any local mechanism. Bell's theorem proves this beyond doubt. The experiments confirm it beyond any reasonable skepticism. But the something that happens is not a signal. It is not a message. It is not information in any usable sense. It is a correlation, a pattern that only becomes visible when you compare the results from both sides using an ordinary classical communication channel that respects the speed of light. To see this clearly, imagine Alice and Bob each have a long list of entangled particles. Alice measures all of hers. Bob measures all of his. Their results are perfectly anti-correlated. Whenever Alice gets up, Bob gets down, and vice versa. But each individual list looks completely random. Alice's list is just a random sequence of ups and downs. So is Bob's. The correlations only become apparent when you put the two lists side by side. Only then do you see that every time Alice got up, Bob got down. But to put the lists side by side, Alice and Bob have to communicate. They have to send their results to each other through some ordinary channel, phone, email, carrier pigeon, and that channel obeys the speed of light. So the spooky action is real, but it is invisible until you bring the two halves of the experiment together. And bringing them together requires ordinary, light-speed limited communication. You might call this the universe having its cake and eating it too. The rules of quantum mechanics are constructed, or perhaps discovered, in such a way that non-locality exists but cannot be exploited. The magic is real, but it cannot be weaponized. Why does the universe work this way? This is a question that physics cannot fully answer. We can describe what the laws are with exquisite precision. We can test them in experiment after experiment. But we cannot explain why these particular laws and not some others. Some physicists believe that the no communication theorem reflects something deep about the nature of space and time. If faster than light communication were possible, it would lead to paradoxes, not just inconvenient or strange situations, but genuine logical contradictions. In Einstein's theory of relativity, different observers moving at different speeds disagree about the ordering of events. This is not a matter of perception or measurement error. According to relativity, There is no absolute simultaneity. Whether event A happens before event B or B before A depends on your reference frame, on how fast you are moving and in what direction. Usually, this does not matter. If event A happens in New York and event B happens in Tokyo, and they are separated by an hour, then everyone agrees A happened first. But if A and B are very close together in time and far apart in space, different observers can disagree about which came first. Normally, this is fine, because A and B cannot influence each other anyway. If neither event could have sent a light signal that reached the other in time, then the ordering does not matter. There is no causal connection between them. But if you could send information faster than light, this ordering becomes crucial. Imagine Alice in New York sends a faster-than-light message to Bob in Tokyo. From Alice's perspective, she sends the message at noon and Bob receives it at 12:01. But from the perspective of an observer flying past at high speed, Bob might receive the message at 11:59, before Alice sent it. This is not science fiction. This is a direct consequence of the mathematics of special relativity. Faster-than-light signals would travel backward in time for some observers. Now imagine Bob immediately sends a faster-than-light reply. From his perspective, the reply reaches Alice moments after he received her message. But from yet another reference frame, Alice might receive the reply before she sent the original message. She could read Bob's answer and then decide not to send the question. But if she does not send the question, Bob has nothing to reply to. Contradiction. These are called closed time-like curves or causal loops. They allow information to travel into its own past, creating paradoxes that have no logical resolution. The grandfather paradox, going back in time and preventing your own birth, is the most famous example. But the information paradoxes are just as troubling. The no communication theorem can be seen as the universe's way of avoiding this catastrophe. Entanglement creates non-local correlations, but those correlations are structured in precisely the way that prevents them from carrying signals. The magic comes with a built-in safety catch. Some physicists argue this is not a coincidence. They suggest that the laws of quantum mechanics are constrained by the requirement of logical consistency, that any theory allowing faster-than-light signaling would contain contradictions and therefore cannot describe reality. From this perspective, the no communication theorem is not just a feature of quantum mechanics, but a necessary condition for any coherent physical theory. Others are more cautious. They point out that we do not fully understand why quantum mechanics has the mathematical structure it does. Perhaps there are deeper principles we have not yet discovered that explain both the existence of entanglement and the impossibility of signaling with it. What then is entanglement good for, if not faster-than-light communication? Quite a lot, as it turns out. The same experiments that proved entanglement is real also laid the foundation for what is now called quantum information science, a field that is transforming computing, communication, and cryptography. Quantum computing uses entanglement to process information in ways that classical computers cannot match. In a classical computer, bits are either 0 or 1. In a quantum computer, qubits can be in superposition, both 0 and 1 simultaneously, and multiple qubits can be entangled with each other. The entanglement is what gives quantum computers their power. When qubits are entangled, they share quantum correlations that allow the computer to explore many possible solutions simultaneously. A quantum computer with 50 entangled qubits can represent and manipulate more than a quadrillion states at once, more than any classical computer could handle. This does not mean quantum computers are universally faster than classical computers. For most everyday tasks, a classical computer is still better. But for certain specific problems, factoring large numbers, searching unsorted databases, simulating molecular structures, quantum computers can offer exponential speedups. The security implications are profound. Much of modern cryptography relies on the difficulty of factoring large numbers. A classical computer would take billions of years to factor the numbers used in secure communications. But a quantum computer running an algorithm called Shor's algorithm could potentially do it in hours or days. This is why governments and companies around the world are racing to build practical quantum computers, and why others are racing to develop quantum-resistant encryption. Entanglement is also essential for quantum error correction, which will be necessary for building large-scale quantum computers. Quantum states are incredibly fragile. They can be disrupted by the slightest interaction with their environment. By entangling multiple physical qubits into a single logical qubit, quantum error correction can detect and fix errors without destroying the quantum information. This technique, still being developed, will be crucial for any quantum computer that needs to run long calculations. Quantum cryptography uses entanglement to detect eavesdroppers. In a protocol developed by Arthur Eckert in 1991, Alice and Bob share entangled particles and measure them to generate a secret key. The protocol is elegant. Alice and Bob each receive one photon from entangled pairs. They randomly choose to measure their photons along different axes. Some of the time, they happen to choose the same axis, and when they do, their results are perfectly correlated. They can use these correlated results as bits of a shared secret key. But what makes this secure? Here is the crucial insight. If an eavesdropper, call her Eve, tries to intercept the photons and measure them, she disturbs the quantum states. Entanglement is fragile. Any attempt to extract information from an entangled particle destroys the correlations that make the protocol work. Alice and Bob can detect Eve's presence by checking whether their correlations still violate Bell's inequality. If Eve has tampered with the photons, the violation will be weaker or absent. By testing a small sample of their data against Bell's inequality, Alice and Bob can verify that their quantum channel has not been compromised. If the Bell test passes, they know, with mathematical certainty based on the laws of physics, that no one has intercepted their photons. They can proceed to use the rest of their correlated measurements as a secure cryptographic key. The no-cloning theorem, which blocks faster-than-light communication, is also what makes quantum cryptography secure. An eavesdropper cannot make copies of the quantum states being transmitted. She must measure them to learn anything, and measuring them inevitably changes them. The same limitation that prevents superluminal signaling provides protection against spying. This is not mere theoretical speculation. Quantum key distribution systems are now commercially available. They have been deployed for secure communications in banking, government, and military applications. In 2017, Chinese scientists used the quantum satellite Michus to distribute entanglement-based cryptographic keys between ground stations separated by over 1,100 kilometers, a distance that would be impossible with optical fibers due to signal loss. Quantum teleportation, which requires a classical channel and cannot outrun light, is nonetheless essential for quantum networks. It allows quantum states to be moved from place to place without physically transporting the particles. This is crucial for distributing entanglement across a network, for linking distant quantum processors, and for building the infrastructure of a quantum internet. The first demonstration of quantum teleportation was achieved in 1997 by Anton Zeilinger's group at the University of Innsbruck and, independently, by Francesco De Martini's group in Rome. Since then, the record for teleportation distance has been extended repeatedly, first across laboratories, then across cities, then across continents using satellites. In 2017, Chinese researchers used the Meichus satellite to teleport quantum states from a ground station in Tibet to the satellite orbiting Curtin of 400 kilometers overhead. In October 2022, the Royal Swedish Academy of Sciences announced that Alain Aspect, John Clauser, and Anton Zeilinger had won the Nobel Prize in Physics. The citation read, "For experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science." The announcement came more than 50 years after Bell published his theorem, more than 50 years after Clauser had begun thinking about how to test it, and 4 decades after Aspect's landmark experiments. The scientific community had long expected this recognition would come. The only question was when. Eva Olsen, a member of the Nobel Committee, said at the announcement that the laureate's work had opened doors to another world and shaken the very foundations of how we interpret measurements. But she also emphasized the practical applications, the quantum computers, the secure communications, the quantum networks that are now being built based on their foundational work. John Clauser, reached by phone after the announcement, recalled his early days working on Bell tests. He had been a graduate student in the 1960s when he first encountered Bell's paper and became convinced that testing the inequality experimentally was important. His professors were not impressed. Richard Feynman, he said, kind of threw me out of his office for suggesting that quantum mechanics might not give correct predictions. Clauser had approached Feynman at Caltech to discuss his planned experiment, and Feynman was offended by the implication that quantum mechanics might be wrong. He didn't consider it a worthwhile project, Clauser later said. His faculty advisors at Columbia thought the experiments were a waste of time, even after the results came in and supported quantum mechanics. "Why, what a waste of time," they said. "You got the results that everybody expected. Now start doing some real physics." But Clauser persisted because he wanted to know the truth. Unlike most physicists of his generation, he took Bell's theorem seriously as a genuine test of quantum foundations, not just a philosophical exercise. Anton Zeilinger, accepting the prize, credited the more than 100 young people who worked with me over the years. He has spent decades pushing quantum teleportation and entanglement distribution to ever greater distances, including demonstrations involving the Chinese satellite Meichus that teleported quantum states between ground stations separated by 1,400 kilometers. Zeilinger's approach has always been to turn quantum foundations into practical technology. He was among the first to recognize that entanglement was not just a curiosity, but a resource, something that could be harnessed, distributed, and used to accomplish tasks impossible with classical physics alone. Alain Aspect, recalled his nervous meeting with John Bell before beginning his experiments. Bell had said something that stuck with him. "Do you have a permanent position?" Bell understood that questioning orthodoxy in physics was risky, but he also understood that the questions needed to be asked and answered experimentally. Bell himself did not live to see the loophole-free experiments or the Nobel Prize. He died in 1990, just as the field he had created was beginning to transform into quantum information science. But he knew, before he died, that his theorem had been vindicated. The experiments of Clauser and Aspect had shown decisively that quantum mechanics was correct and that no local hidden variable theory could explain the correlations. He was a very gentle man, Aspect later said of Bell, but also very rigorous and very demanding in terms of physics. Einstein would have been frustrated by these results. He spent the last decades of his life searching for a unified theory that would restore common sense locality to physics. He never found it. The universe, it seems, is not built the way he wanted it to be. In letters to friends, Einstein expressed his discomfort repeatedly. "I cannot seriously believe in quantum mechanics," he wrote to Max Born in 1926, "because the theory cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky action at a distance." Nearly 30 years later, his view had not changed, but Einstein would also, perhaps, have been gratified by one aspect of the story. He was right that entanglement had profound implications. He was right that it deserved careful scrutiny. He was right that the foundations of quantum mechanics mattered. The EPR paper that he wrote in 1935, proposing what he thought was a reductio ad absurdum of quantum mechanics, turned out to be the seed of an entirely new branch of physics, and he was right about one crucial thing. Whatever spooky action existed in quantum mechanics, it could not be used to send signals faster than light. Einstein believed this because he believed the spooky action did not really exist, that it was an artifact of an incomplete theory. He was wrong about that. The spooky action is real. But he was right that no information flows faster than light. The universe respects causality even as it violates our classical intuitions about locality. This is perhaps the strangest aspect of the whole story. Einstein's intuition that faster-than-light signaling must be impossible was correct. His conclusion that therefore quantum mechanics must be incomplete was wrong. The universe found a way to have both: genuine non-locality that does not enable signaling. Einstein could not imagine such a thing. Neither could anyone else until the mathematics of quantum mechanics revealed it. So where does this leave us? The universe is stranger than Einstein wanted to believe, but saner than our science fiction dreams suggest. Entangled particles really are connected in ways that cannot be explained by any classical mechanism. Measurements really do seem to affect each other instantly across arbitrary distances. The fabric of space and time, at its most fundamental level, is woven with threads of correlation that defy simple physical explanation. Yet these correlations come with a constraint that preserves the logical structure of the universe. They cannot carry information. They cannot transmit messages. They cannot be used to communicate faster than the speed of light. The non-locality is real, but it is a non-locality of correlation, not of communication. Some physicists describe this as passion at a distance, rather than action at a distance. The entangled particles share a connection that is passionate, intimate, correlated, mysteriously linked. but they cannot act on each other in any way that transmits information. Their bond is real but impotent, profound but ultimately private. Others describe it as quantum non-locality, being non-local without being non-local. The correlations transcend space, but no signal crosses the gap. It is as if the universe allows particles to whisper secrets to each other that we can never overhear, conversations that influence nothing and yet are undeniably happening. This is not a disappointment, it is a wonder. The universe has given us something that our pre-quantum physics said should be impossible. Genuine, non-local connections between distant particles, while withholding something that would have broken causality. It has expanded our understanding of what is physically possible, while maintaining the coherent structure that allows physics to exist at all. Perhaps the deepest lesson is about the relationship between correlation and causation. We are taught that correlation does not imply causation. The two things can be statistically related without one causing the other. Entanglement takes this principle to its logical extreme. Entangled particles exhibit correlations that are stronger than any classical mechanism could produce, stronger than any local cause could explain. Yet these correlations are not causation. Nothing travels between the particles. No influence propagates. There is simply correlation. Bare, unexplained, undeniable correlation. This challenges our intuitions about what it means for things to be connected. We think of connections as physical, wires, forces, signals passing through space. Entanglement shows us a different kind of connection, one that has no physical mediator, one that exists in the quantum state itself, rather than in the space between particles. The next time you hear about quantum entanglement, remember this: the spooky action is real. Einstein was wrong about that, but no message travels along the invisible threads that connect entangled particles. The correlations are not signals. The magic cannot be weaponized. The universe keeps its deepest secrets while still, somehow, letting us glimpse its astonishing architecture. You live in a cosmos where particles can be mysteriously connected across any distance, yet where information still respects the speed of light. Both things are true. Both things have been proven in experiments that close all the loopholes and eliminate all the doubts. This is not a contradiction. This is just how the universe works. And understanding that, really understanding it, is perhaps the closest we can come to touching the true strangeness of the quantum world. The connections are real. The spooky action is real. But the messages we might dream of sending across those connections will never arrive. The universe allows us the wonder of non-locality while denying us its exploitation. That limitation is not a flaw in our understanding or a gap in our technology. It is written into the fundamental laws of nature as deep as the speed of light itself. Einstein wanted a universe of definite properties and local causes. He did not get it, but he did get a universe that still, in its strange quantum way, respects causality. He was wrong about the spooky action, but right about the impossibility of faster-than-light communication. In the end, perhaps that is the most surprising thing of all, that these two facts could both be true at once, that nature could be so strange, yet so structured, so non-local, yet so safe. We are left with a universe more wonderful than any science fiction, more mysterious than any philosophy, and more rigorously tested than any speculation. Quantum entanglement is real. faster-than-light communication is not. And that somehow makes the whole thing even more remarkable.